Okay, so this is question number 4, and first one is really straightforward. I won't spend much time on question number 1. I'll just straight away and quickly write what it is equal to, and that's what we get here. Next one is straightforward. Again, you need to find mod 10 over z, and then you need to take mod. So first we'll find 10 over z, which is 10 over 1 plus 2 iota. Now, before you can find its conjugate as indicated by this bar here, you need to convert that into x plus iota y form. So we know how to do that. We just multiply with the conjugate of denominator. So 1 plus 2 iota, 1 minus 2 iota, 1 minus 2 iota, and that gives you, if you just multiply, that becomes 10 minus 20 iota divided by 1. I'll get real term by multiplying real and imaginary parts. So 1 times 1 is 1, and that minus 4 iota square. 2 iota minus 2 iota is minus 4 iota square. And then you got imaginary part by multiplying imaginaries with the real. So that's minus 2i plus 2i. So that becomes 1 plus 4, which is equals to 10 minus 20 iota divided by 5, and the final answer that we get is not final answer, I mean that 10 over y is equals to 2 minus 4 iota. Therefore now if you take its conjugate, you do this, and answer is 2 plus 4 iota. So simple enough, and let's move on to next question. It's not very difficult. So now we got these things, 1 plus root 3, and it says question B, but it's part of question number 4, but it's not related in any way with part A of question number 4, so it's totally independent, basically starting from here. Okay, so here now again you need to think. You're trying to find alpha over beta. You're doing a division, and in complex number, the division and multiplications are better, are easier basically in the polar form. So you need to convert both alpha and beta into polar form. You could do that, and the other option would be to just do it algebraically in the Cartesian form, and we could use that as well. So let's use Cartesian form here. Alpha over beta, what we get here is 1 plus iota root 3 divided by 1 plus 1 iota. Again, to write it in the form x plus iota y, so what we do is we multiply with the conjugate of the denominator, and I'll quickly write here without spending much time. That becomes 1 plus 1, and then that's the real part, that's the imaginary part, divided by 2, and your final answer then is 1 upon root 3 upon 2 plus iota root 3 minus 1 over 2. That's your complex number in x plus iota y form. When we say x plus iota y form, basically all we want is in Cartesian form. Now we need to write alpha in modulus argument form. So alpha is given as 1 plus iota root 3. And whenever you try to convert something into polar form, into modulus argument form, I strongly recommend that you draw a diagram to see in which quadrant your complex number lies. So if we see here, just a rough sketch diagram, 1 plus iota root 3, this is 1, that's root 3 here. This is root 3, this is 1, so we need to find, that's the argument of this theta here. So mod alpha is equal to square root of 1 mod alpha is 1 square plus root 3 square, that gives you 1 plus 3 is equals to 2, and from diagram theta is equals to tan inverse root 3, which gives you pi over 3. So simple question, alpha is equals to 2 cis pi over 3. Next part is beta is already given in this form. So basically it is given, I mean, if you look at this, beta is now root 2 6 pi over 3. So this time we are finding alpha or beta using polar form. So alpha upon beta, if you remember the very first part, we found alpha or beta in the Cartesian form, and this time we are finding in polar form. So alpha in the polar form that we found was 2 cis pi over 3 from previous, just part 2 here, and this one gives us root 2 cis pi over 4, so that becomes root 2 cis pi over 3 minus pi over 4, and what you get is root 2 cis pi over 12. Alright, so that part is alright, and then we go to part 4, which is here. Hence find the exact value of sine pi over 12. So we need to take a look here that we got, if you look at part A, we found alpha or beta is equals to this here in part 4 B1, and in part B3 we found that alpha over beta is equals to root 2 cis pi over 2. So both are alpha over beta, so we can equate these values. So what we have, alpha over, okay, so let's start again. Alpha over beta, from part 1 it was let's take part from part 3 plus part 3, alpha over beta is equals to root 2 cis pi over 12, and from part 1 alpha over beta is equals to, we already found that. I have these values here. It says root 3 plus 1 upon 2 plus iota root 3 minus 1 over 2. This implies, I mean, I can write this polar form into Cartesian form now. So I get root 2 cos pi over 12 iota root 2 sine pi over 12. Let me scroll it a little bit up, and that is equals to root 3 plus 1 over 2. Now we got two complex numbers which are equal, so obviously their real and imaginary parts should be equal, but we only want the value of sine pi over 12, so we'll just equate the imaginary parts. Again, you need to write equating imaginary parts. What we have here is root 2 sine pi over 12 is equals to root 3 minus 1 over 2, and that tells us that sine pi over 2 is equals to root 3 minus 1 over 2 root 2, and that's our answer here. Okay, that is simple. Then let's look at the last question here as well. Find the smallest positive value for n if alpha over beta to the power n is real. So in these kind of questions, because it's a division, you need, and you're raising to the power n, you need it to be in polar form. So we'll use the polar form alpha over beta, which we already found in part 3 above. So alpha over beta is equals to root 2 cis pi over 12. Therefore, alpha over beta to the power n is equals to root 2 to the power n, and that becomes root to the power n cis n pi over 12. Now, for this to be real, this n pi over 12 has to be along the real axis. So this argument of this complex number has to be either 0 or pi. So for this to be real, cis n pi over 12 should be equals to 0 or equal to pi or 2 pi, and like that. Yep, so when you look at that, oh sorry, not cis, the angle, I'm just talking about the argument. The argument should be equal to this. So that gives you n is equals to, you got 0, 12, 24, and likewise. Therefore, the smallest positive value of n is equals to 12, and that's your answer. And that is question number 4, and we are going to stop at that.